Okay, guys, let us consider this part of the alternator, the alternating current machines, which is one of the most important part of our syllabus. So the first part that you are going to need according to your syllabus is to work or to deal with the general expression for the EMF of an alternator. So as we had the DC machines before, there is quite a lot of things that you're going to see that has changed from our DC machines. You were having the EMF equation. We talked about calculations where the EMF equation is to be used. But in this case, considering the EMF of an alternator, let us just have this. That is the EMF equation. All right, so we're going to consider the EMF equation of an alternator. So what is it that I need to know about this alternator, which is the part of our DC machine calculations? I mean, the AC machine calculations. The EMF E is equal to, according to our formula sheet, you're going to have 2,222. Then we have got the product of the constant, which is the distribution factor, the product of the pitch factor, the product of the number of conductors, the useful flux, and the frequency. So as you can see, this formula is totally different from the DC machines. It's totally different. So what is it that we have? So like I said, this is the EMF, as we know that our EMF is measured in what? In volts. So we've got KD, which is representing the distribution factor. So this is the distribution factor. So we're going to talk of the distribution factor of the windings. All right, so we've got the distribution factor of the winding, which you're supposed to be given. Then Kp, which is the pitch factor. So in that case, we are talking about the pitch factor of the winding again. So this is the pitch factor of the winding. So this is what you actually need whenever you are given this. And whenever you are given a condition where you're dealing with a full pitch winding. For a full pitch winding, all right, so you're going to have this condition for a full pitch winding. In this case, you are going to use Kp equal to 1 whenever you are dealing with a full pitch winding. Kp must be equal to 1. All right. There is a frequency, the flux, so forth, that we need, the useful flux, remember the Z being the number of conductors. So this is the number of conductors. So you are going to take this according to the condition that you're given there. There's a condition that you'll be given. You use that to determine the number of conductors. And as we know, our useful flux from our DC machines in Webers, and we've got F, which is the frequency. This time working with AC, we need the frequency. So like I said, there are some of the things that you need. The number of conductors, you work that according to the condition that you're given. According to the number of conductors, you work with the condition that you'll be given. We're going to explain that. Then both the frequency, as you can see on our formula, there's a frequency there. So in most cases, you are going to find out that maybe you are not even given the frequency, but you need the frequency. And they need you even to calculate that. So you can calculate this from the synchronous speed. All right, so we have got the synchronous speed. All right, these ways, do not worry about this. So just N, the speed is equal to the frequency over the pair poles. The speed measured in revs per second is equal to the frequency. Remember your frequency in hertz, and P is the pair poles. That is the number of pair poles that you are given. If you are given 6 poles, then our P will be equal to 6 divided by 2, which is 3 pairs, just like what we had from our DC machine, right? So meaning to say you'll be having 3 pairs. So with this formula, the speed being in revs per second. So remember any, if you're given any, you have to convert that any to revs per second. So any in revs per second is equal to any over 60. That is to convert to revs per second. You divide the any which is in revs per minute by 60. All right. So with the same formula, you can calculate, you can make the frequency the subject. If you just cross multiply, it means frequency is equal to NP. You can make P the subject. If you divide by N, it means P is equal to F over N. So this formula can be given in any way. So for you not to have a misunderstanding, just know one formula. From that formula, manipulate other formulas, but just know one formula, okay? So this is what you're going to have. And this part, the E that we are talking about is going to be the E, which is represented as the RMS value of EMF per phase. This is per phase. So you're talking about the RMS value of EMF per phase, per each phase. The same as the number of conductors, they are taken per phase, per each phase. Remember AC, we have got single phase, 3 phase. So that's why we talk about this. That's why we represent or talk about this. So it follows that given, let's say, I have got the E, which is the generated EMF. Let's say I am given a certain value of E. It follows that the E per phase, which is the one that you need on your on your formula there, is equal to E over the square root of 3. Remember from our star connection, the voltage of the line is equal to the square root of 3 times the voltage of the phase. So per phase you divide, so you just divide by the square root of 3, the square root of 3. So that means the voltage per phase is equal to VL over the square root of 3. So this E is the line voltage. We're talking about the line voltage. All right. Then E per phase, that is the generated EMF per phase. This is the idea of what? The star connection. The same, we are going to need the impedance per phase according to this part. This Z that we have, it's per phase. So let's just can even write as ZP, EP like this, which is taken as the phase voltage, the phase impedance. So for the phase impedance, it's going to be the total number of conductors over 3. You divide by 3. That is the total number of conductors from the given condition. So this is the total number of conductors, the total number of conductors from what? From the given condition. There is a condition that you'll be given from the given condition. All right. So you work with the given condition to determine the number of conductors. Then to determine the number of conductors per phase, you divide by 3. Okay. Sometimes they will even ask you to calculate the turns per phase. The turns per phase. As per the turns per phase, it is equal to the Z per phase, the number of impedance that we had per phase over what? Over 2. This one that we got after Z dividing by 3, the answer that you have the number of conductors per phase divide by 2. So this is simply number of what? Of conductors per phase. Just like that. So like I said, the total impedance is going to be affected with a certain condition that you'll be given. I don't know the given condition that you're going to have, but you must use that condition to answer your question. So we want to check how questions are given and how are we going to use this idea, the formula of which is the EMF equation of the alternator, and also including the synchronous speed of an alternator, and also the idea of the phase concept, the generated EMF per phase, the impedance per phase. I mean the number of conductors per phase. You see now, guys, this thing of working with the other part of Z being taken as the impedance. No, this one we are representing to the number of conductors per phase. So let's see. We are given a typical question that we have here. A 3-phase, like I said, remember this is AC machines. It can be single or 3-phase. So this is a 3-phase. So we have to consider those square root of 3 whenever you're dealing with a 3-phase. Single phase, there's no need for you to change anything because remember we're saying per phase. So if it is a single phase, the Z that you have is that there's no other calculation that you take. So for a 3-phase, you have to be very careful. All right, so this is a 3-phase. So we are given this here that is a 3-phase star connected. So this is a star connected alternator driven at the speed which is in revs per minute, 1,200 revs per minute, is required to generate a line to generate. It is the generate, but for the line voltage, which is the generated from the line. So you can even just maybe write EL, but I think I talked about these guys, remember, from your 3-phase star. VL for the line is equal to square root of 3 VP. So as we are saying, this is E for the line, then E, which is taken for the phase, is the one that you are presenting as E per phase, which is the one that we said to obtain this, you have to divide the one for the line, divided by what? By the square root of 3. So take note of the information. This is the line, but generated. So this is E generated of 885 volts, which you can write even as EL if you just maybe have a misunderstanding. But this is just E for the line. Just know that this is the line generated voltage or the line generated EMF. So what about E per phase? Because the E per phase is the one that I need on the formula. The formula here does not take the E of the line. The formula, I said it takes the E per phase. This E is the RMS value of the EMF per phase, not the line voltage, but it must be the phase generated EMF. So we saw that it is E over the square root of 3. So that is 885 over the square root of 3. So this is the one that you need. All right. At a frequency of 60 hertz, the frequency is given as 60 hertz. So there's nothing to change there. Just going to take our frequency as it is at 60 hertz. Open circuit. Assume full pitched coils. Whenever you are talking about this, it is going to affect the pitch factor of this one, of the winding, Kp. For a full pitch winding, your Kp must be equal to 1. because it's full. So this one, they are saying assume it's a full pitched coils. So we are given the pitch factor there to be 1. So the pitch factor will be equal to a 1. Then you are given, okay, I'm going to talk about this statement. Let us just take KD, which is the distribution factor. We are given our distribution factor as 0.96. So this one is given 0.96. All right. Then, like I said, you need to understand the given condition there. They are saying, please be very careful. Be very, very careful. They are saying, and the stator has 8 slots per pole, per phase. All right. It has got 8 slots per pole, per each pole. But not just only that, per phase. Per phase. All right, let me just write it this way so that you understand me. So they are saying we are given 8 slots per what? Per pole, per phase. This is the first condition. And and 6 conductors per slot. Per slot. So this is another condition. And 6 conductors per slot. Okay. Meaning to say we skipped something about the poles there. So the question is, okay, we are not given the poles, so we're going to calculate that one. That is what they want as 5.41. So you need, because it's referred 8 slots per pole. So you're going to need the number of poles, which you do not have. So it is going to be difficult for us to obtain our Z. But this is the information that you are going to use to obtain the Z. So let's just leave it for now because we do not have the number of poles. As you can see, the poles are included. So let's leave it like that because we're going to need that on 5.31. Calculate the number of poles. So you wonder, how can I calculate the number of poles with this formula alone? Guys, remember I talked about the synchronous speed. N is equal to the frequency over the pair poles. With this formula, we can be able to calculate the pair poles. Then we can calculate the number of poles. So 5.41, we saw that N, the synchronous speed in revs per second, is equal to the frequency over the pair poles. So it follows that as we need not the pair poles, but the poles. So you first find pair poles, which is P. So you can even make P the subject, cross multiply. NP is equal to F. So divide by N both sides. So P, which is the pair poles, is frequency over N. Like I said, this N is in revs per second. And I also talked about converting revs per minute to revs per second. It's N over 60. N in revs per minute divided by 60. All right. So meaning to say, this was going to be equal to the frequency, which is 60 over N, which is revs per second, but they were given in revs per minute. So you're going to divide that by 60. So that's 1,200 over a 60 like this. This is giving us revs per second. All right. So this is going to give us the P, which is pair poles. P represent pair poles. P on this formula, this P, I said it's for pair poles. Pair poles, not the poles, but the pairs. There are 3 pairs. So if there are 3 pairs, how many poles are we having? That is the question. If you have 3 pairs, therefore, how many poles that we have? Therefore, there are 6 poles. Remember, from the pair poles, It's just going to be times 2. How are you finding the pair poles? If you are given 8 poles, you divide by 2 to determine the pair poles, like 4 pairs. This time we've got pairs. So to obtain the number of poles, you multiply by 2. 2 times 4, that is 8. So this is what we were just having there. So be careful. You have the pairs, then you've got the poles. These are 2 different things that we are given, okay? So that's our 5.41. It was to calculate the number of poles, not the pair poles. Okay, so we now know that we've got 6 poles. I'm just going to remove this since we now know this, okay? There are 6 poles that we have, meaning to say our pairs, there are 3, but the poles, there are 6. So we have got poles, which is 6, but the pairs, remember we said we have got 3 pairs if you divide by 2. All right, so the question was now to calculate the useful flux per pole from the generated EMF of an alternator. We have got the useful flux per pole. But as we can see our formula there, okay, let me just write our formula, then we're going to explain that. Remember, I said something that you need to use on this formula. 5.42. The generated EMF being equal to 2,22 times, we've got the constants or the coefficients or the constants there, KD, which is the distribution factor, the pitch factor, the phase impedance, the useful flux, and the frequency. So like I said, this is EP per phase. This is ZP per phase, per phase. Take note about that. Per phase. So since you need the useful flux here, you are going to divide by this here and also the frequency, both sides. All right, remember from your mathematics. So the useful flux is going to be EP, which is the generated EMF per phase, not the line, but the generated one. So you're going to divide by 2,22 times KD times KP times the Z per phase times the frequency, the impedance per phase. So let's start with the EP. Are we having EP? Remember, we are given the E, and I said per phase, it's a star connection, divide by the square root of 3. So this is, we have this, KD, we are given, KP, for a full pitch, it's going to be 1, all right? Then we do not have this, going to calculate this, we do not have this part, the frequency is given. So ZP, which is the phase, which is the number of conductors per phase. Remember, I talked about this. Z per phase, which is the number of conductors per phase, is going to be equal to the total number of conductors divided by 3. So we need the first Z, which is the total number from the given condition. There is a condition that you are given. And what is the condition? The condition is, okay, let us get to our condition. They are saying there are 8 slots per pole. This is the condition now. 8 slots per pole per phase. Per. If you are given like, let's just say 8 slots per pole. Per pole means like you multiply by the number of poles to obtain the number of slots. So you start, the one that is at the beginning here is the one that you obtain. 8 slots per, all right? 8, so it's 8 slots per pole per phase. So let's start with that one. Let's start with this one. So how many slots? The number of slots. The number of slots. They are saying there are 8 slots per pole per times the number of how, because guys, per means per each 1 2 3 4 each. So if there are 2, you multiply by 2. If there are 3, you multiply by. So how many poles? Because it's per pole. How many poles? 6. There are 6, not per poles, but pole, not per poles. per pole times the phase. How many phases are we having? It's a 3-phase. Remember, it's a 3-phase star. So how many phases? There are 3. So it's a 3-phase. Per phase, and we've got 3 phases. So you multiply by 3. So this is going to give us just the slots, the number of slots, only that. Only that. The number of slots only. So we've got 144 slots. But now take note. They are saying and. It's another and. That's another condition that you're given there. And this is another condition. And 6 conductors per slot. So let's talk about the conductors now. Z is equal to what? If they are saying there are 6 conductors per, I said per, you multiply by the number of that per slot. So it's 6 conductors times the number of slots. How many slots? 144 slots. So this is going to give us the total of 864 conductors. These are the number of conductors. So this is just like what we had for the voltage. When we say this is the EMF voltage, so it's just like for the impedance. I mean, for the number of conductors also. Back in that part, just like for the number of what conductors. So each and every part, be careful how it is given. Each and every part. All right. So very sorry for that. So I was saying the Z is the number, the total. Just like you're taking at the line, but now per phase, because this is the total number of conductors. But we said we must now obtain per phase. So let us go back here. Z per phase is going to be the total number of conductors from the given condition. Then you divide by 3. You are now determining the Z per phase, which is the one that you need on the formula. This ZP is this per phase, this one. So to determine the ZP, the one that you need on your formula there, it is going to be Z over 3, the total number of conductors that you calculated divided by 3. So you can even leave it like this, or you can even calculate, which is going to be 288 conductors per what? Per phase. So this is the one that you are going to use. The 288 on this formula, we need the phase values per phase, the EMF per phase, the number of conductors again per phase. If you are using another formula which has got the tens, you use the tens per phase. So this is going to give us the useful flux in what? In Webers. So the useful flux is equal to EP per phase. Remember I said here, E per phase is going to be 885 over. So dividing by the square root of 3, it was going to give us a decimal. It can affect our answer, but no what, if you can do that, just leave it like that. All right. Or you can just write as it is 885 over what? Over the square root of 3. All right. So divide these two, the rest of the formula that you're given, as we now calculated ZP. So you're going to have KD, the distribution factor of 0.96, the pitch factor 1, then ZP per phase. This is 288 times the frequency, which is 60 hertz. So that is the idea there. So you must be very, very careful how you are going to present your values. So this was going to give us a decimal 0.01386, like that. If you want to write it to 3 decimal places, you write the Webers, which is fine. If you want to convert to milli-Webers, you multiply times 10 to the exponent of 3, which is the opposite. Remember, milli-Webers times 10 to the exponent of -3. So the opposite now is the one that you use to convert to milli-Webers. So by multiplying by 10 to the exponent of 3, we are converting to milli-Webers automatically. All right, so that's our useful flux, which was going to be 13,862 to 3 decimal places milli-Webers. So it's no longer as direct as it was when you're dealing with a DC machine. It was just direct, you subs, this time you need to calculate this, find this, and substitute into the formula that you're given. So you must be very, very careful how the information is presented or given. How the information is given is the most important thing. All right, let us consider another question where we are given again another similar question, just a little bit similar, not the same, but a little bit similar. A three-phase. So this is a three-phase. So according to the information that you're given, it's a three-phase. How many poles that you're given? 6 pole. So this is a 6 pole star connected. So remember from the pair, the poles, you can even determine the pair poles 6 divided by 2, meaning to say we've got 3 pairs. Okay. It's a star connected alternator delivers 425 volts between lines on the open circuit. So this is VL for the line, or this is E for the line. I don't know the way that you're going to take. Are you going to take it as E? Are you going to take it as V? But this is for the line. So what you need on the formula is the E per phase, which is the phase, or just the phase. You can even just write EP if you do not want to have a mistake there, which is E over the square root of 3. Remember, it's a star. In a star, the line voltage is equal to square root of 3 phase voltage. So you need the phase generated EMF. So it was going to be 425 over the square root of 3. So this is the one that you are going to use on your calculations. This is the one that you use. Running at a speed of 1,000, we are given the speed 1,550 revs per minute. There are 2 conductors per slot and 3 slots per pole per phase. The condition there again with that condition. So in this case, let us start with because this one I think everything is there because we've got the poles are there actually. So they are saying there are 2 conductors per slot. There are 2 conductors per slot. So this will give us the number of conductors. Let's leave it like that. Let's talk about the slots. And there are 3 slots per pole. So let's talk about the number of slots. How many slots do we have? There are 3 slots per pole. How many poles? 6. So you multiply to the poles. Per phase. How many phase? 3 phase. So this is just about the slots. This is about the slots only. So there are 54 slots. But what about the conductors now? They are saying there are 2 conductors per slot. 2 conductors per slot. So it's 2 times per slot times. How many slots? 54. Just like that, you're done. So this will give us 108 conductors. All right. So that's 108 conductors. But remember what I said about this, you're going to need ZP, which is the phase, just like EP for the phase. You're given E, but you need EP. On the formula, you take phase values. So the ZP was going to be 108 divided by 3, which is 36 conductors per watt per phase, which is the EP. All right. So that's what we heard about this. And we are also given if the winding is a pitch factor, this time you're given the pitch factor of 0.8 and the distribution factor of 0.96. So you're also given the distribution factor 0.96. Assume a sine wave. Calculate the frequency. Okay, this is it. Calculate the frequency. I said there is a relationship that you're going to take from the synchronous speed because you are given the speed. Remember that part of the synchronous speed. The synchronous speed in revs per second is equal to the frequency over the pair pulse in revs per second. So the question is, can we calculate frequency from here? Yes, because we've got the pair pulse. Over 1, just cross multiply. So 1 times F is going to be frequency is equal to NP. So frequency is equal to N. Remember the N is small letter, revs per second. They were given revs per minute, divide by 60. 1,550 divided by 60 times the pair pulse. How many pair pulse do, the pair pulse, which is here, we divided, the pair pulse is what? Is 3. Not the pulse, but P. Whenever you use P, it's pair pulse. P is for pair pulse. Just like that. So this was going to give us the frequency, which was going to be 77.5 hertz. So this is your question. You asked to calculate the frequency. So you got your frequency. So your frequency was 77.5 hertz. Okay, so maybe you're gonna need this frequency. Let's just leave it like that. Just like that. This is how these questions will be given. All right. The turns per pole. Okay, about the turns per pole, we talked about this. If you check here, I talked about this. The turns per pole, that is the one they tend to talk about, which is the turns per phase. So meaning to say you're going to need Z per phase over 2, of which you calculated ZP, which is ZP you calculated here. Remember your ZP. So it was going to be part of this calculation of the ZP that you had here. It was going to be part of this calculation also. So that is the turns per pole. According to what they gave us, they are saying per pole, that means per phase. That is ZP over 3. All right, so that is over 2, sorry, over 2. The over 3 is converting Z to ZP. But to convert to the tens, you take the ZP, which is the number of conductors per phase, 288 divided by 2. So this will give us the tens per pole. This will give us per pole. Guys, you see now, sorry, very sorry for that. You see, I'm answering. I took this formula. Let me just delete. I'm now answering on the wrong part. I hope someone just saw this and was like, what is happening? Let me quickly remove this page, guys. You see, this part now, I was even surprised. Why is this answer now different here, guys? This is our question here. So this is our ZP. Sorry for that. Very sorry for that. So that's 5.22. So like I said, the question was now given as the turns per phase, which is per pole. That is ZP over 2. So our ZP, we calculated that was 36. Then you divide by 2. So that means we've got 18 turns per pole. So that was the question there. That is how you answer this one. You take it from the number of conductors already that you have per phase. The one for phase, that is the one that you work with. Then you just divide by what? By 2. Okay, so that was also a direct question because you have this. But the 3 marks is because you were not having the ZP. So if you have not calculated this, then you have to calculate. But if you've calculated, they're going to check that one from your calculations that you have before. Then the useful flux per pole, if you check this question, we are now back to the generated EMF, the one that we had before. Remember, from our generated EMF, I said AP, which is the phase, is equal to 2,22 times KD times KP, Z per phase. Then we've got the useful flux, the frequency. So this is phase. So we need the useful flux per pole, as we saw, guys. We're going to divide. That is EP divided by everything, which is 2,22 KD KP. ZP, then the frequency. So everything we have, and this will give us our answer in Webers. All right, so the useful flux was going to be E taken per phase, which is E, we said per phase is going to be 425 over square root of 3 from the line voltage that you're given. So that's 425 over the square root of 3. So there we have got the phase generated EMF 2,22 times, remember, your distribution factor is given 0,96 kp, 0,8. This time you're given this. So that's 0,96 times 0,8. Then the Z taken on our phase, remember ZP, we calculated this and got 36. That is 36 conductors in the phase. That is 36 times the frequency, which we also calculated from that part, and we got 77,5. So we're going to use the value that you calculated. Remember, we got 77,5, just like that. So if you just need your answer to be converted direct to milliwebers at this point, just multiply by 10 to the exponent of 3. This is to convert your answer straight to milliwebers. So meaning to say, whatever that I'm going to have, if your calculator is to, you have changed your calculator to 3 decimal place, whatever that you're going to have there, it is now in milliwebers. So that was going to be 51,537 to 3 decimal places milliwebers. That is the useful flux per pole. So these are the typical exam questions. So if you check your syllabuses, guys, whether it's mathematics, is what, they just give you a few parts that you just need, like formula, this and that. The next question, they are taking that question exactly the way that they're asking in these question papers. So you see that the more you do question papers, that's the best. The first example that you check in your textbook, it's a typical exam question. The first example, it's a typical, where have you learned it? So the more question papers, actually, that is the more you understand it. The terms, you have heard these terms from your N4, now do as many questions as you can. So that's it, guys, from Maison African Motives. Till we meet again.